Typically in life, we're not really dealing with simple constructions like point charges. What we really care about are the electric fields due to oddly shaped objects. Charged objects in life are just not effectively modeled as point charges. So if you had some object and the object contained some amount of charge, then how would you determine the electric field at some point due to that object? Or at any other point for that matter? I think we should start with something simpler though, namely a thin line of charge. This is a charged object with a uniformly distributed charge Q and a length L. Uniformly distributed means if we divide this line into any number of segments, all of equal length, each segment has exactly the same amount of charge. Another way of illustrating the same idea is that a uniform linear charge density of lambda naught means the charge per length of any segment is exactly the same, no matter how long or short the segment is, provided that segment has a non-zero length, of course. What is the electric field at point P, a point that lies midway between this line a perpendicular distance of a away from it? It's not so simple, because up to this point we only have knowledge of the electric field due to a single point charge and multiple point charges, but not charged objects like this line here. So one idea we have is that the object is really just made up of a collection of small amounts of charge, isn't it? So if we can just find out what the electric field vectors are due to each of those small amounts of charge, then we can just add up all those little vectors to get the total electric field. But there's just one problem. These little amounts of charge that make up the line, we can't just willy-nilly call them point charges, can we? Because at the end of the day, they are really just charged objects too. What we end up with is a decent approximation for the true electric field if we just treat them like point charges, but we can do a little bit better. What if we presume each segment to be really small? So small that each segment is infinitesimally small. Each charge now has some unfathomably tiny value dq. Now, provided the line of charge is actually thin enough, calling each of these dq's a point charge is an extremely good approximation to the true electric field. We can't hope to do any better than this without making the problem unreasonably difficult for ourselves. We need to integrate this electric field dE based on the charge dQ over the entire line, and that'll give us the electric field at this point. Also note that I'm wildly exaggerating the size of dE here. In reality, it's so small you can't even see it. We're in a hairy position, however. You see, this isn't like one of those normal integrals you're used to dealing with in your calculus classes. This integral has a vector in it, and this vector, r hat, it changes depending on which dq we're looking at. This might not be the worst integral in the world to evaluate if we didn't have to deal with that pesky r hat. If we have a positive charge dq, we expect r hat to be the unit vector that points away from dq, and that determines the direction of dE. You might be thinking, I don't want to solve that integral. Well, welcome to the big leagues. We'll explore the line charge problem in one of our exercises. So for now, why don't we start with something a bit more tangible and we'll work our way up from there. Suppose, for example, that we had a thin ring of radius capital R and uniformly distributed charge throughout of capital Q, and we were interested in finding the electric field at the dead center of this ring. You might even have a feeling as to what the electric field should be, but let's try to work it out anyway. The first step when dealing with a charged object is for us to be humble and remind ourselves that we don't know how to find the electric field of anything, except a single point charge or multiple point charges. So how do we turn this problem into a problem of multiple charges? Provided the ring is thin enough, an infinitesimally small charge dq is virtually a point charge, and the electric field it creates at the center is given by this expression here, where r hat points away from dq. Remember, once again, dE is so small that it's actually invisible, but I'm making it really large here just for the sake of illustration. To find the electric field E, we need to add up or integrate all the dE's together. The distance from each dq to the center of the ring is always capital R, the radius of the ring, so we can pull out some of the constants and we're left with this strange looking integral here. K and capital R don't change with dq, but r hat sure does, so we can't exactly pull it out of the integral just yet. It's not constant. To simplify further, we can't really do much with dq yet either, but we can try to think of what r hat might be in terms of some angle theta, for example. R hat is a unit vector that points away from the direction of dq if dq is positive, since the electric field points away from positive charges and towards negative charges. If we had a vector b in 2 dimensions, for instance, we recall this vector can be written as the magnitude of b times cosine of theta times I hat, plus the magnitude of b times sine of theta times j hat. If the magnitude of b happened to be 1, then we could call it b hat, and it's just cosine of theta I hat plus sine of theta j hat. Since r hat actually points opposite to b hat for a given theta, we care about the negative of b hat, which is the true direction for the electric field. We find that r hat, the vector we were really after in the first place, is just the negative of this vector b hat, which we were talking about here. Now we're kind of stuck though. We have an integrand that's a function of theta, but the differential is dq. In order to evaluate this integral, we either need to figure out how to transform theta into q somehow, or transform dq into d theta somehow. It turns out the latter is much easier to do than the former. We have to get our integral in terms of a single variable so we can integrate, and defining a linear density of charge is going to help us out here. The linear charge density of this ring could be written as the total charge of the ring, q, divided by the total length of the ring, the circumference, which is pi times the diameter, or 2 pi r. Now, the usefulness of such a definition comes about when we consider different segments of the ring. In general, if we have some circular segment, the length of that segment is given by delta s equals r times delta theta, where delta theta is given in radians. So if we have some tiny segment dq, infinitesimally small, then the linear charge density of this segment is given by dq over ds, or dq over r times d theta. That helps us find dq in terms of d theta. We've just done all the hard part, the rest is easy, we just have to carry through with the integration. So the answer we get is the electric field at the dead center of the ring is 0, or rather, the 0 vector. In hindsight, it seems kind of obvious that we would have ended up with 0 though, because of the symmetry in the problem. For every dq on one half of the ring, there's a dq on the other side of the ring completely canceling out any net electric field contribution. Adding up this arrangement of electric field vectors is 0 for any pair we choose on each side, and since the combination of all pairs gives us the total electric field, we end up with a net 0 electric field at this point. All that work for a not so exciting result, eh? So let's see if we can spice things up a bit. For your next exercise, consider the same problem of finding the electric field, only at a different point. A point moved away from the center of the ring, but still equidistant from all of the other points on the ring. As a hint, consider the distance from this point to any of the other points on the ring as defined by a certain right triangle. Another hint, now that we're dealing with a three-dimensional problem, we should end up with E having an x component, y component, and z component. Oh dear, can we simplify this immediately off the bat? Should any of these components be 0 by symmetry, in which case we only have to determine the non-zero components, or a component. If you've never seen this problem before, it's a heavy one, so good luck.